Alright, so this is test 2 from Calculus 1 of 2010. I'm not really going to explain everything in here. I mean, I have posted the solutions and the blank ones are there for you to work through. I just want to kind of comment on anything that needs further comment. Let's see here. Uh, Usually, this pi cubed, people just want to do 3 pi squared. Every generation of Calc 1 students falls into this trap. Sorry. Anyway, so that's that. That's a minus 3 halves that we can't quite see there. A, B, and C are assumed to be, oh, they're not assumed to be constants. B is a variable here. X and A and C are assumed to be constants. So when you differentiate with respect to B, you just get back X. It's kind of an interesting problem. Here's a product rule. Actually, it's product and chain, right? At the top here, I think I said differentiate, don't simplify. Complete the indicated derivatives if more than one variable is present in the expression. We assume the variables are independent. I guess the point is here I didn't ask you to simplify, so you don't have to. If I have something like this, and I say don't simplify, let's just agree that if I say simplify, I want you to simplify, and if I say otherwise, it's understood that you should just complete the calculus and stop there, because tests don't have a lot of time. So if I want you to simplify, I'll probably say simplify. Anyway, invariably people will waste oodles of time trying to multiply this out, where all I really care about is seeing that you understand the product rule and the chain rule like that, another derivative, A, B, and C are constants here. And this one, this is chain rule followed by basically well, there's another chain rule to get the 14. That's because 2 times 7 is 14, Derivative inverse sine, 1 over the square root of 1 minus the thing squared. Then chain rule brings out the 3e to the x. This next one is by the quotient rule, right? Quotient rule, and there's some chain rule stuff going on with the e to the minus 2x up here. Over here, actually. So derivative of x is 1, derivative of e to the minus 2x is minus 2 e to the minus 2x, but there's a minus, so minus minus gives me plus. You should also be able to do problem 3. How do you show the derivative of a to the x is natural log of a times a to the x? Well, you can show that using implicit differentiation, much like we've discussed, right? Y equals a to the x, take the natural log of both sides. Now, it's presupposed here that the derivative of natural log is known. This problem would be better if I said you're given that the derivative of the natural log is known. Show this, all right? So, not. I don't know. I always debate whether less is more or more is less in writing a test. If I write too much, then you guys are distracted by all the words. And if I write too little and you're careful, you might get stuck where I don't intend you to get stuck. So I don't know. There's some kind of balance to be struck there. But anyway, there it is. That's how to derive that formula, which I have quoted. Problem 4. You are given standard trigonometric identities, and that the limit of sine and cosine, as written there, are given. Prove that the derivative of sine x is cosine x. There's a bad bracket here. That bracket's supposed to be over there, right? And so this is just from the definition of derivative, how to show derivative of sine is cosine. Again, that was appropriate for the course because we talked about that. I think, as I think about a quick review of Calc for Calc 2, I don't really have this in mind so much. I mean, I would like you to know it, but all right. This is something you should be able to do. How do you differentiate x plus cosine to the sine of x? Well, that's an implicit differentiation problem. However, what you got to do is you got to split it up into 2 problems, differentiate the x and differentiate that separately. When I gave this problem, it stumped a lot of the class. People don't have in mind this divide and conquer idea as much as they should. Logarithmic differentiation, I haven't talked about, but it is something you should know about, so I encourage you to review it. Basically, the idea is, I say I haven't talked about it. I haven't talked about it in the nutshell review of Calculus 1 I've been putting together at the moment, but if I was teaching Calc 1, I'd talk about this for several days. But in short, you just take the natural log of some complicated expression like this and use properties of logs to simplify, like this. And then it's easy to differentiate these because the derivative of a log is, well, it works out, it does, and so it gives you this, and then you just multiply both. And then this differentiates to 1 over y dy dx, so when you multiply both sides by y, you get that. So this logarithmic differentiation. Implicit differentiation, so you find dy dx by differentiating this, and then solving for dy dx after you've done the implicit differentiation. And then to find the tangent line, you just plug in x equal to 1, y equals to 2 into this expression, and then go back to how we find the tangent line to a curve, right? The y value plus the slope times x minus the x value. There it is. Approximate the fourth root of 17 by considering the linearization. Linearization is nothing more than what? The linearization is the function whose graph is the tangent line. So that's really just a question about using the tangent line to approximate the function. The function here is the fourth root of x. The reason I say fourth root of x is because we know the fourth root of 16 is 2. That's just, oh, I kind of guided them to doing that, didn't I? So there it is. Let's see here. Argue for or against the following claim. Let's see here. F is a differentiable function on R. Well, the derivative of cosine plus 1 and cosine minus 1 definitely exists away from pi over 2, but at pi over 2, that function's not continuous because cosine pi over 2, of course, is 0, but plus and minus 1 don't match from the left and right, so it's not continuous. If it's not continuous, it can't possibly be differentiable, all right? Some guy named Frank tells you that P is equal to mv. If you're given that dp dt equals 10 and dv dt equals 3, when m equals 1 and v equals 2, at what rate is m changing? Oh, fun. So this is a related rates problem. Definitely fair game for the quiz. Problem 11 didn't make sense, so I figured it out during the giving of the test, and I gave them options, but let's just skip it. Problem 12. If a function f is continuously differentiable at a point in the domain such that f prime of a is not equal to 0, what does this tell you about the function? Well, if the derivative is continuous, if it's non-zero at a point, it means it's non-zero near the point. All right, so if the derivative is non-zero near the point, and it's got to either stay positive or stay negative, in other words, the function's either strictly increasing or strictly decreasing near the point, which tells me that a local inverse exists near the function, near that point. That's what that means. That's kind of a challenge theory question there. Now we're getting into the more challenging part of the test. Let P be a polynomial function, degree n greater than 1. Define f of x equals P of x e to the cx, where c is a constant. How many horizontal tangents are possible? I have not talked about horizontal tangents, which is unfortunate. Horizontal tangent is simply a tangent line which is horizontal. What's the horizontal line slope? Well, it's 0, right? So basically, to find horizontal tangents for a function, all you gotta do is look for where is the derivative 0. So I set df dx equal to 0, and then I have to differentiate, by the product rule. And I got e to the cx both places, so I just factor it out. So basically, I'm looking at dp dx plus cp equal to 0, since e to the cx is non-zero. But so this is an nth order polynomial, and then we know from the theory of polynomial equations that has at most n real zeros. So there are j horizontal tangents where j has got to be something between 0 and n, and that's about all I can say with that much data. Problem 10? What? Oh, these are unnumbered. I guess that's problem 13. Problem. We've got a function u. This notation means, if you ever have a question about notation, just ask me during the test, C2, that means twice continuously differentiable. So g of u is sinh of u squared. U is a function which is given to be differentiable twice over, but that's all we know. And we were looking at this other function g, which is the h of x is g of u of x, all right? Calculate dh dx. So that's the chain rule. H prime prime, we differentiate this again, have to use the product rule and the chain rule. We get this monstrosity down there. And then horizontal tangents. Well, horizontal tangents have to be where dh dx equal to 0. If you look at the formula for h prime, back up here, we have u cosh of u squared du dx. So cosh of u squared is never 0. So in order for this to be 0, either u would have to be 0 or du dx equal to 0. Yeah, like I said, either u equals 0 or du dx equal to 0, or both, of course. That's where you'd find horizontal tangents, and that's the answer, because that's all you can do with the information which is given. And I think that's about it. This was a pretty good section of Calculus 1, so I did try to ask some more difficult questions at the end of the test, and if I don't ask difficult questions at the end of the test, you shouldn't be happy. That means I'm insulting you. Anyway, thanks.